Welcome to the community of
engineers, the change agents in the society.
In this video, we will derive expression for the generalized Hooke's law. So far, we have considered only the uniaxial loading, but what will happen for the case of multi-axial loading? Let us consider a structural element made up of homogeneous and isotropic material. Assume the element is cubic, equal to unity on each side. Now the member is subjected to multi-axial loading, considering loading along all the three coordinate axes. Due to this loading, the stresses are produced along the x-axis, along the y-axis, and along the z-axis. Due to this multi-axial loading, the member will deform into rectangular parallelepiped, where each side is equal to 1 plus epsilon x, 1 plus epsilon y, and 1 plus epsilon z. Here, epsilon x, epsilon y, and epsilon z are the normal strains along the respective axes. Now these strains are expressed in terms of stress components. For that, Hooke's law is used in combination with the Poisson's ratio using the superposition method. So the strains caused by the strains caused by the stresses along x-axis going to be using Hooke's law as epsilon x is equal to sigma x divided by Young's modulus. Even though there are no stresses acting along the y and z direction, but there are strains in these directions as the material contracts in the lateral directions. The strains in lateral directions are obtained by multiplying the longitudinal strain with the Poisson's ratio as we discussed in the last session. So the strain along y-axis is going to be minus nu Poisson's ratio with the longitudinal strain sigma x. Similarly, epsilon z is equal to minus nu epsilon x. These expressions could be rewritten as the epsilon y is equal to epsilon z is equal to minus nu. Now using the value of this epsilon x as sigma x upon Young's modulus E. Now the strains along x-axis is going to be sigma x upon E minus nu sigma y upon E minus nu sigma z upon E. Similarly, the strains along y-axis are going to be minus nu sigma x upon E plus sigma y upon E minus mu sigma z upon E. Now the strains along z direction are going to be epsilon z is equal to minus nu sigma x upon E minus nu sigma y upon E plus sigma z upon E. Now these expressions are showing the generalized Hooke's law. These can also be rewritten as epsilon x is equal to 1 upon Young's modulus into sigma x minus nu sigma y plus sigma z. Similarly, epsilon y is equal to 1 upon E sigma y minus nu sigma x plus sigma z. Same way, epsilon z is equal to 1 upon E over sigma z minus nu sigma x plus sigma y. Now we will discuss the dilatation and the bulk modulus. Due to the effect of normal stresses sigma x, sigma y and sigma z, the cubic element will deform into a rectangular parallelepiped. Consequently, the deformed volume would be the product of the deformed volume V is the product of 1 plus epsilon x, 1 plus epsilon y and 1 plus epsilon z. Since the strains are much smaller than the unity, so the product can be omitted from the expression and the expression could be rewritten as V is equal to 1 plus epsilon x plus epsilon y plus epsilon z. Whereas the change in volume that is represented with E is going to be the deformed volume V minus the original volume. Now using the value of deformed volume, the expression is written as 1 plus epsilon x plus epsilon y plus epsilon z minus 1. Now after cancelling this 1, the final term that is the change in volume, that is epsilon x plus epsilon y plus epsilon z. Now here the change in volume per unit volume is known as the dilatation of the material. Now using the values of strains in the equation of dilatation, that is E is equal to epsilon x plus epsilon y plus epsilon z. Now using the values of generalized Hooke's law in this expression, we have that is 1 upon E sigma x minus nu sigma y plus sigma z plus 1 upon e sigma y minus u sigma x plus sigma z plus 1 upon e sigma z minus nu sigma x plus sigma y. Now, by rearranging the expression, this could be written as E is equal to 1 minus 2 nu upon E sigma x plus sigma y plus sigma z. Now, by considering each component of stress as the uniform hydrostatic pressure P, this expression could be written as E is going to be 3 1 minus 2 nu upon E times P. Now, by introducing another constant of bulk modulus or the modulus of compression of the material, this is K and its value is E upon 3 1 minus 2 nu. Now, using this expression or substituting this the modulus of compression or the bulk modulus in the expression of dilatation, we have the final expression that is of E is equal to minus P upon K, the Young's modulus. Now here the negative sign is for the hydrostatic pressure, considering that there must be decrease in the volume for a stable material. So with this we will end our discussion here.